Let me quiz you a little bit more. What about the magnetic field along a line that's maybe slightly above this or slightly below? What about magnetic field along this line? Will it still be straight? Or do you expect it to bend? Be straight. Can you explain how you would prove that the magnetic field along this line should also just point straight into the right instead of curving one way or the other?
Because the line or the current is still within inside of the solenoid.
Yeah, that doesn't prove anything because, I mean, the direction for this, that comes from your intuition. So when I say prove, it's a request for a mathematically rigorous argument. As in, I'm going to take role of a skeptic, someone who's going to say no to everything. If you tell me the grass is green outside, I'm going to say no. There's a section that I cannot see. So that's what you have to imagine. When I ask you to prove something, that's the standard that I'm applying, that I'm going to have unreasonable doubt, and you have to be able to overcome that. So here, the intuition you have is that you have a ring. And you know the magnetic field for a ring of current, right? You have seen this before. Magnetic field for just a ring of current would look like, so in the center, it was straight. But when you go away from center, it kind of looped around these other currents. That's what you saw before. You had this dipole field when you had the ring before. So that's why I'm asking you to prove. So in the center, it makes sense to me that it's straight. There's nothing else it can be. But I'm asking you to prove that somehow the magnetic field here doesn't bend the way I saw it bend for a ring. Sorry, what? Okay, so if you have this intuition that this is producing a field like this section is producing field like this, and you think they will all add up to give me a straight line, that's not wrong, but it's not a proof. So what argument would you use to prove that the only direction the magnetic field can point in is the straight line parallel to axis to the right? That there is no way it can sort of point at some angle, that only component of magnetic field you can have is along the axis. This argument is something that we have been making. Maybe not explicitly every single time. This time I'm asking you to make it explicit because it's so easy to just step over it and not learn how to make this argument. I mean, superposition is where this intuition comes from, that I'm imagining magnetic field due to each of these rings adding. So that's why I think, okay, it sounds reasonable to me. So I think it could be true. Unless I can say that I don't ask you to prove something, because it's silly to try to prove something that you are not even sure if it's true. But once the word proof is said, then what I'm looking for is now a mathematically rigorous argument. Something where I can simply say I don't believe that, without also saying I don't believe in logic. Once again, this is a symmetry argument. What kind of symmetry argument would you make to say there is no way that magnetic field along this line can be anything but something that's parallel to the axis? It's Chris.
Any point along the line, the vertical components of them cancel out, and it's just
cancel out how? I don't believe it'll cancel out.
Oh, well, that circle that you have on there that you're erasing right now, that.
Yeah. So you are making plausibility argument. Unless you are ready to break up Biot-Savart's law and actually vector calculus calculation, I'm not accepting that. Yeah, because you are making a plausible argument when I'm asking you to do a proof. Yeah, and there's a way to prove this without doing complicated math. So once again, this is what I'm asking. Let's just take a single point. Taking a single point here, this is what I'm asking you to prove. Let's say I'm going to, whatever magnetic field is here, let's say I'm going to decompose it into two components. A component along the axis and a component that's potentially perpendicular to the axis, right? And I'm asking you to prove that this must be 0. at every single point along this line. Okay, what does it have? What does infinitely long? The thing being infinitely long have to do with the perpendicular component being 0. Cross product means nothing to me right now. So once again, it's a symmetry argument. So, okay, so what are the symmetries that are present in solenoid? So there's a rotational symmetry, and I assume you mean this symmetry, as in you can take this axis that's going through the center of the solenoid, or none of my solenoids are big enough. Well, if take the axis that's going through the center of the solenoid, then when you rotate, then it doesn't, then nothing changes. All right, what else? Yeah, translational along the axis. So, all right, which of those two symmetries could you use to argue that this perpendicular component should be 0? Yeah, translational. So this is where you imagine if so you imagine these magnetic field lines. So if you had this perpendicular component, then at some point, this is what the magnetic field line would look like. If you had the perpendicular component, at some point your magnetic field line would look like this, right? And what translational symmetry means is that the strength of magnetic field here should be the same as the strength of magnetic field at this point. From this field line, does it look like they have the same strength? No. Which side is magnetic field stronger? Left side or right side?
Left side.
Why left side?
The distance is shorter.
Yeah, so when the field lines are denser, that's where they are stronger. So that's inconsistent with translational symmetry. So the only way, so this is how you prove things. So I guess this is called proof by contradiction, where you assume the opposite of the thing that you're trying to prove. So you are trying to prove that this has to be, perfectly parallel. So you assume the opposite thing. You say it's not parallel, meaning it has some angle. And you reach a conclusion that's contrary to what you know to be true. In this case, the translational symmetry, that the magnetic field strength at this point should be the same as magnetic field strength at this point. So once you reach this contradiction, that's when you know the thing that you assumed was wrong. If you ever take logic class, you can work through how this works. But this is a method called proof by contradiction. So the first thing, the initial thing I assumed must be wrong, which means, the only way it can be is parallel. Yeah. So, I guess it depends on the level of math you go at. And I will tell you this much. I know a number of engineers who's in engineering graduate school. And even for engineers, once you're at high enough level, you have to know how to do proof arguments. So, lower division, it's not common that you see proof level argument. The proof is usually upper division level work at a minimum, even if you're a math major. But you have to start at some point. You have to start thinking that, we don't always do things rigorously. Like in physics, oftentimes I'll do hand-waving argument and move on. But this is one of the few cases where proof actually matters, where being able to demonstrate without any shred of doubt what you are trying to say is true, that you need to start developing that ability. This is like algebra skill, except at a more abstract and higher level. So you can make the exact same line of argument for a line that's down here. So with those set of arguments, what you can say is that magnetic field inside the solenoid is straight throughout the entire volume of the solenoid, and it points in that one direction. What about the magnetic field outside the solenoid? I know Monday, I told you that we'll prove that magnetic field outside the solenoid should be 0. But let's say magnetic field outside the solenoid wasn't 0. What direction should it be? Opposite direction, also in a straight line? Yeah, for the same reason. Because this is has a translational symmetry. Or to go back to the original reason, because this is infinitely long. That's the symmetry that a single ring doesn't have. That's why with a single ring, there's all this differently bending magnetic field. But once you, gather up enough of these to give it a translational symmetry, then all these other perpendicular directions of magnetic field has to go away. So magnetic field outside, if there is any, will go the other way. Right? Well, we are on a roll. Let's finish it for toroid. I'm hoping we can actually finish all 4 geometries today. Yeah?
So there is or isn't a magnetic field outside?
We are going to start. So once again, this is the matter of principle when you are doing proof. I want to prove that the magnetic field outside is 0, which means there's one thing that I'm never allowed to do. I'm never allowed to assume that magnetic field outside is 0. The moment you assume it, you have given up on proving it. But I can assume the opposite. I can assume that magnetic field outside may not be 0. And then if I reach some kind of contradiction, or so that's what I'm doing here. Yeah. So as long as I'm trying to prove that magnetic field outside is 0, I'm never going to assume it. I'm going to show it from some other things I know to be true.